So today I'm going to talk about secondary stability and periodicity for unordered configuration spaces. These are some homological stability patterns for unordered configuration spaces on a manifold. Before I say a little bit about secondary stability and periodic stability, let me begin by reviewing a little bit about classical homological stability. So for this part of the talk, M is going to be a connected open manifold. Open here just means compact. Not compact is a topological space. And M will always be connected throughout this talk. My main object of study is the configuration space of k unordered points on M, and I'll always denote this by conf k of M. Now, since M is open, there's a map called the stabilization map from the configuration space of k points on M to the configuration space of k plus 1 points on M. And the way sometimes this is known as bringing a point in from infinity. The idea is you sort of fix an embedding of Rn, where n is the dimension of the manifold, disjoint union the manifold into the manifold itself, and you bring in a point that way. So a result dating back to McDuff from the 1970s states that for M, a connected open manifold, the stabilization map sigma from the configuration space of k points on M to the configuration space of k plus 1 points on M induces an isomorphism on integral homology from homology in degree I of configuration space of k points on M to homology in degree I of configuration space of k plus 1 points on M. And this induced map is an isomorphism as k grows large in comparison to the homological degree I. And there have been a lot of, in my opinion, there have been a lot of improvements in this result, in that later work due to Graham-Siegel, for example, gave some explicit bounds in which sigma induces this isomorphism, and later on in other work by, for example, Oscar Randal-Williams, for instance, and work of Jeremy Miller and Sandra Kupers, gave some improved ranges when, for example, you want to look at homology with with rational coefficients, for example, or over a finite field FP. And I guess what I'm trying to say is that we have very sharp bounds in which sigma induces this isomorphism when M is an open manifold. Yeah, so now I want to say a little bit about some more recent stability phenomena. And the first one I want to talk about is something known as secondary stability. So secondary stability was first described in work of Soren Galatius, Oscar Randal-Williams, and Alexander Kupers in their work on the mapping class groups of a surface. A key feature of homological or of secondary stability is that homological degree is no longer fixed. A way I guess I would try to say what it's about is you're sort of trying to figure out if there's some sort of pattern for the unstable homology groups, and the way you look at this pattern is by trying to find some sort, trying to detect if the homology groups of the mapping of the cone configuration space of k plus 1 points on M relative to the configuration space of k points on M stabilize in some way. So in homological stability, the statement that you have homological stability in some range is equivalent to the homology of the mapping cone, the homology of the mapping cone where, or the relative pair, the configuration space of k plus 1 points on M relative to the configuration space of k points on M is 0 in some range. And so secondary stability wants to study the case when you might not have that this cone is, the homology of this cone is 0 in a range, but maybe you'll have that it's an isomorphism. Unfortunately, I don't have a lot of time to say a little bit more about secondary stability, but one result I have that I guess could be described as secondary stability is the following. So let M be a connected open surface. Then there is a map, which I'll call S2, from the homology in degree I of the cone of the relative pair of the configuration space of k plus 1 points on M relative to the configuration space of k points on M with coefficients over the finite field over a finite field of Fp, where Fp is the field with p elements for p and odd prime. And so this is the target of this map is homology in degree I plus 2p minus 2 of the relative pair of configurations of k plus 1 plus 2p points on M relative to the configuration space of k plus 2p points on M. And this map is an isomorphism in a range, specifically for k greater than, for this range right here, which I won't specifically say. But yeah, and the way there is a relatively explicit explanation of where this map comes from. The way I would sort of visualize it is, whereas homological stability can be visualized as bringing in the class of 1 point near the boundary. Here you're bringing in a 2p minus 2 parameter of, or parameterizing family of 2p points on of a disk, and you're somehow stabilizing by this parameter family of 2p points. But yeah, so the next stability pattern I want to discuss is something called periodic stability. So up till now, everything that I've been talking about has been concerned with the open case when M is an open manifold, and it's reasonable to ask, is there homological stability of some kind when our manifold is no longer open, i.e. it's like a closed manifold. And here, by closed, I just mean that the manifold is compact as a topological space and doesn't have any boundary. So there's two issues that need to be addressed. So the first issue is that if M is a closed manifold, there does not exist an obvious candidate for what a stabilization map should be from the configuration space of k points on M, the configuration space of k plus 1 points on M. And I mean, this is definitely like an issue because the stabilization map really does depend on M being an open manifold. But yeah, so that's one issue. And the other issue that I think is a more fatal issue in my opinion is that we shouldn't expect to even have homological stability, as the following example shows due to work of Vidal and Van Buskirk. And so in this example, they showed that the first homology of the configuration space of k points on the two-sphere, and here I mean integral homology, this is an abelian group, is isomorphic to Z mod 2k minus 2 for k at least 2. So, you might think that we can't have any sort of hope here for some sort of homological stability, but if you sort of squint at this example, you realize you won't have homological stability, but if you look at things mod, like, you will have some sort of periodic stability in that if you looked at homology over the field Fp, then you would have some sort of, you wouldn't have that the configuration space in degree 1 of conf k of S2 is isomorphic to the first homology of the configuration space of k plus 1 points on S2. But you would see that the homology of the configuration space of K plus P points on S2 is isomorphic to the homology in degree 1 of the configuration space of K points on S2. So even though there's an issue integrally when we reduce to a finite field FP, this problem goes away. And a good way of a bunch of other people, specifically Federico Quintero and Martin Palmer, some work of Rohit Nagpal and Jeremy Miller and Sandra Kupers, show that for M-connected closed manifold, we have this abstract isomorphism between the homology in degree I of the configuration space of K points on M with, here I mean with FP coefficients, is abstractly isomorphic to the configuration space in degree I of K plus P points on M. And this isomorphism holds as K grows large in comparison to I. And I think it's a reasonable question to ask if there's some sort of map on, if there's some sort of stabilization map between the configuration space of K points on M to the configuration space of K plus P points on M, which induces this isomorphism. And to my knowledge, I don't know if there is such a map, but what I was able to do actually was produce a map on the chain level between chains on the configuration space of K points on M, and here I mean chains with FP coefficients, and so I was able to produce a map from chains on that space to chains on the configuration space of K plus P points on M with FP coefficients. And doing that, one can show that you have periodic homological stability for a closed connected manifold. But something that I think is kind of nicer is that instead of getting just ordinary periodic homological stability for a closed manifold, we can actually obtain periodic secondary stability for a closed surface. The reason why we don't really get periodic secondary stability for higher dimensional manifolds is because in dimensions 3 and above, we already get an optimal stability range for homology with FP coefficients. So looking at secondary stability, for example, doesn't give you any new information. So we're only interested in the dimension 2 case in this case. And the result that I obtain is the following. So let M be a connected closed surface, and now there's a map. You should think of this as being exactly analogous to the secondary stability map from a few slides ago. So there's a map which it is basically exactly the same as before, but now instead of looking at the relative pair, where the relative pair consists of the configuration space of K plus 1 points on M relative to the configuration space of K points on M, and with FP coefficients, I want to look at the configuration. Now I want to look at the configuration space of K plus P points on M relative to the configuration space of K points on M. And I should have added probably, by the way, that the map in this case is coming from this new stabilization map on chains on the configuration space of M. So I'm looking at chains of the configuration space of K plus P points on M relative to the configuration space of K points on M, of chains on the configuration space of K points on M under this new stabilization map on the chain level. And you get that it's an isomorphism in the same range as before. So with the time I have remaining, let me just give a proof sketch for how one would prove periodic secondary stability. So for this part, M is going to be a closed surface, and M is just going to be an open disk in our manifold. So we have that for a general manifold, not just a surface, that the configuration space on M can be broken up into the configuration, a bar construction involving the configuration space of M with the closure of the disk removed and the configuration space of S1 cross the closed interval from 0 to infinity and the configuration space of points on a disk. And I'm being a little bit sloppy here. You have to change a little bit of the structure of the configuration spaces on the right-hand side of this bar thing, but I don't have that much time to go into it. I think the main sort of thing here is you want to think about configurations on the cylinder S1 cross 0 to infinity as sort of like a monoid object in spaces, and configurations on the disk and on M with the closure of the disk removed as modules over the configurations on the cylinder. And on the right-hand side, basically the way you sort of make the proof work is you just have to reduce to producing a stabilization map for chains on the configurations on the configuration space on the disk. And here I mean configurations with FP coefficients. And the important thing here is that you want this stabilization map to preserve the algebraic structure of configurations on D as viewed as configurations on as a module over configurations on the cylinder. And then that I think is probably the hard part and the interesting part of the proof. And then once you do that, you can get an ordinary stabilization map as well as a secondary stabilization map pretty easily. And yeah, that's all I want to say. Thank you for listening to my talk.